So last lecture I didn't realize I had an hour and a half, so I thought I only had an hour. I won't be making that mistake again. All right, so at the last lecture we finished deriving the SUSY algebra. So it's just just looks like that, okay? And I said that for the homework exercise, you could try to check the Jacobi identities with including the Poincare algebra. Okay, so let that be problem number 1. Yeah, so that's something you could try at home. Now, Michele suggested that I spend little time reviewing the notation and all that, and that's probably a good idea so that you can follow the rest of the lectures, hopefully. And so if you've seen this all before, then just bear with me for 10 or 15 minutes. Okay, so logically, this what I'm about to say comes before any of this. Okay, this assumed you already knew what I'm about to say. But anyway, so let's do a quick refresher of the representations of SO3, 1 and the alpha, alpha dot, etc. notation. Okay, so just the basic fact that starts everything is the fact that the Lorentz group is mathematically SO3, 1, which after you go to Euclidean space is SO4. All right, and SO4 is actually isomorphic to SU2 times SU2. All right, so that's the basic fact that starts it all, if you like. Okay, so being SU2, 2 copies of SU2, we know what to do with that, right? That we learned in kindergarten. So we know what to do with 2 copies of SU2, and so the representation, the irreducible representations of SU2 are labeled by a single integer j. Sorry, not integer. It could be half integer. Okay, so j is either integer or half integer. And the dimension of the representation, which is just the possible values that the z component can take, is a spin, z component spin, so that gets you 2j plus 1. Right? Okay, so those are the irreducible representations of a single SU2, and SO4 has 2 copies. So we have, it's conventional to call this one left-handed and that one right-handed. Okay, so this is SU2 left, SU2 right. And so each of them has its own j in principle. And so the irreducible representations of the Lorentz group are labeled by 2 integers, j left and j right. 2 half integers or half integers, j left and j right. Okay. So I should probably have said, why are we going through this representation theory? It's because this being a symmetry group of nature, all the particles and fields have to transform as representations of this. Right? That's how symmetries work in field theory. Okay. So we know that the particles and fields are going to be classified, they're going to fall into these irreducible representations of SO4, and so this is the basic math problem that we have to solve. Right? So, for example, so these are the 2 integers, and this is all possible irreps of SO4. So you're already familiar with some examples, right? So a scalar, so spin 0 is 0, 0, right? You can have 1/2 0. What is this? This is a left-handed vinyl fermion. You can also have 0.5. This is a right-handed vinyl fermion. You can check the dimensions, right? Work out. And then 1/2, as we said last lecture, this is a vector. Okay, and so we usually stop with that. And so the notation is something that's important to master, I guess. And so this is, the scalar is not interesting, but the fermion we usually denote, this is how we usually denote a left-handed Bow fermion. It has one index alpha, okay? Alpha here runs from 1 to 2, and so it reflects the two possible spin orientations. This is a two-dimensional representation, right? 2j plus 1. Two-dimensional representation, so that's why this alpha goes from 1 to 2. Okay? And so the right-handed Bow fermion we usually denote with a tilde, some people use a bar, and an alpha dot. Okay, so that's something to get used to as well. So the dotted indices refer to the right-handed transformation properties. Okay, and then as we said in last lecture, one way to talk about the vector boson is to write it as A alpha alpha dot. Okay. Stop me if you have any questions at all. How many people have seen this before? Oh, so everyone's seen it. Okay, let me accelerate it then. I was only going to spend 10 minutes on sitting here. Okay, so alpha dot also runs from 1 to 2. We can form Lorentz invariants. So we form Lorentz invariants by using what's called the invariant tensor. So that's epsilon alpha beta, epsilon alpha beta dot. These are the totally anti-symmetric tensor. Right, so that's the invariant tensor of SU2. And so we also use this to raise and lower indices, right? So we have psi alpha with a raised index is epsilon alpha beta psi beta. And psi little alpha dot is epsilon alpha dot beta dot. Like that. And then by multiplying together raised and lowered indices, we form Lorentz invariants. So like this is a Lorentz invariant object, okay? So is this, for example. Okay, so Lorentz invariant objects are ones in which all the indices are contracted. So you're probably familiar with that also from GR. All right. Okay, so, and this is of course used heavily when you come to form Lagrangians, right? So Lagrangians have to be Lorentz invariant. All right. So another invariant symbol is sigma mu alpha alpha dot. I should say a good reference for this. If you ever need to look any of this stuff up, I like to look in Srebnicki, his textbook, which is also freely available online on his website. And so that's a good place where all these things are collected. Okay, so another invariant symbol is the Pauli matrices plus the identity, right? So sigma mu alpha alpha dot is 1 is the identity matrix, 2 by 2 identity matrix, and then the 2 by 2 Pauli matrices. Okay, and so this thing converts these alpha alpha dot indices into mu indices. Okay, so using this thing, we can write this also as like that. All right, and another conventional notation is to introduce the friend of this, sigma bar, which has raised indices, and we raise and lower again with the epsilon tensor. So this is defined to be sigma mu beta beta dot epsilon beta epsilon alpha dot beta dot. Okay, so this is something I'll use a lot. Okay. So good. So let me also mention briefly how tensor products work. Okay, so you know from SU2 that one way you can build up bigger and bigger representations of SU2 is to take the fundamental representation of SU2 and tensor it together, right? And I can make bigger and bigger representations by continuing to do that. Right? So that's a quick way of generating big representations. And so we know that, for instance, if I take 2 times 2, this is equal to 1 plus 3. Okay, so in other words, the tensor product of 2 fundamental representations is not itself irreducible, okay, but it decomposes into irreducible representations. In this case, it decomposes into the singlet representation and the triplet representation. Okay, so this is j equals a half, and then this is j equals 0, j equals 1. So we all know that from like quantum mechanics, for instance. Okay, so using this index notation, that's a quick way also to get this answer. So if I represent psi alpha and this as, say, chi beta, and I just multiply them together, okay, I just ask, how do I make an irreducible representation out of this tensor here with these 2 indices? And there are basically 2 ways to do it. It can either be proportional to epsilon alpha beta times some number, well, not some number, some, well, whatever we call this thing, field times another field, okay? Or it could be, sorry, let me just call this A. Or it could be some object B alpha beta, where, so if I take this part out, okay, this is the anti-symmetric part, right? And then this is the symmetric part. Okay, so in other words, this is psi alpha chi beta anti-symmetrized, and then this is psi alpha chi beta symmetrized. Okay, so using the epsilon tensor and continuing to use that and subtracting out the anti-symmetric parts, you can reconstruct all the irreducible representations of any tensor product. All right. This is the singlet, and this is the triplet. Okay. So what else can I say? So yeah, one other important thing is how these things transform under the Lorentz group. So the other nice thing about this index notation is that transformations under Lorentz are dictated by indices. So once you know what indices your field carries, you know all the Lorentz transformation properties. Okay. So for instance, well, okay, so consider a field with some indices. Let's just say a collection of indices denoted by A, capital A. Okay, so for instance, for a spinner, this could be alpha. For a vector, this could be alpha, alpha dot. I'm just going to denote them all collectively by capital A. Okay, so this thing, under this, just knowing what these indices are, and if this is irreducible representation, then you know how this thing is going to transform under the Lorentz group, right? That's the whole point. So, in general, the way we talk about those transformations is as the commutation relations with the generators, Lorentz group, right? And so, what does this have to be? Well, this is the whole thing about a representation, right? So this has to be given by some, basically some transformation, well, some linear operator acting on phi A that represents the Lorentz group, okay? That composes in the same way as the Lorentz group does. Okay, so this has two pieces to it in general. There's the piece that transforms the space-time coordinate x. Okay, so there's some piece that transforms the space-time coordinate x, and then there's another piece which transforms these indices A and B. Where this thing here is just some derivatives. Okay, so this part is always the same for any field, any type of field. And then this part here depends on the representation of the field in question. Okay, so this is some matrix of matrices, if you like. So it's got this matrix here, and then it's also got this matrix here. So probably an example is good. So, for example, if we're talking about, suppose we're talking about a left-handed Weyl fermion. Okay, we're talking about a left-handed Weyl fermion. Then this thing just has, you know, a one index here and one index here. Okay, that runs from 1 to 2. So what is this object going to be? Well, I should have said this has the same commutation relations as M. Okay, that's what it means to be a representation. Okay, so whatever this is, this matrix of matrices. So this is a quantum operator, right? This is some differential operator. These are just a collection of pure numbers, basically. It's a bunch of matrices. And these matrices have to have the same commutation relations as mu nu. And maybe you're used to 4-component notation, for instance, if you study Peskin. And what are these things for that? Those are the gamma matrices, right? Well, not quite. They're made out of the gamma matrices, sorry. Actually, they're going to be similar to what I'm going to say right now. So what is this thing that has the same commutation relations as mu nu? Turns out to be sigma mu bar nu. Okay. In fact, that's sort of the simplest thing you could write down. Well, the only thing you could write down, I think, with the right index structure. Okay, and then the I over 4, the I even is determined by the hermiticity properties, and the 1/4 is just a normalization to agree with the commutation relations of n. Okay? So you might be used to seeing this in the Clifford algebra form, where, in the 4-component form, this is gamma nu, like that. Okay? This is the same thing. Okay, I think I should probably move on. So I just had one more thing prepared about Lagrangians, but How many people know the difference between Majorana and Dirac fermions? So most of you have seen that before. Yeah, okay, I think I'm going to skip that, and I'll get back to the Lagrangians when we come to construct SUSY Lagrangians. Maybe I'll review that, put that part of the review in there. Okay. Are there any questions? This is like really fundamental stuff, so the rest of the lectures are going to depend on it. So if you have any questions about it, now I'll give it to you fast. Okay. All right. So getting back to the supersymmetry and the SUSY algebra, so we've constructed the algebra here, and now we'd like to know, what's the next thing we'd like to know? Well, just like we did the representation theory of the Lorentz group, we'd like to do the representation theory of the SUSY algebra, right? So, and the irreducible representations of that, or even the non-irreducible, in general, any representation of the SUSY algebra is going to be what's called a supermultiplet. Okay, so if things transform into each other under supersymmetry, then they live in a multiplet. Okay, and supersymmetry is going to relate the properties. Okay. So. Okay. So these generate a space-time symmetry. Well, and more generally, they generate a symmetry. Okay, so what does that mean? Just like we had mu nu commutators with the fields gave us the transformation of those fields under the Lorentz group, we also can consider commutators of Q alpha with, say, some field. Or Q alpha here is fermionic. Okay, so if that field is fermionic, then this has to be an anti-commutator. Sorry, an anti-commutator. Okay, but either way, we can consider these things. And these are the transformations of that field under supersymmetry. Okay? And supersymmetry is this weird thing. It's generated by fermionic symmetry. So unlike the Lorentz transformations, which have a classical analog, right? They correspond to boosts and rotations. So we could do that classically. Here, this has no classical analog. Okay? So supersymmetry, even though it's a space-time thing, it has no classical analog. Okay, so there's no way to make sense of it, just by thinking about trains and clocks and things. Okay? All right. Nevertheless, we can use the same mathematical tools that we use for Lorentz symmetry or any other symmetry to describe how supersymmetry works. Okay, so these commutators or anti-commutators correspond to the symmetry transformations. And so right away, we see that SUSY relates particles with different spin. Okay, so supersymmetry transformation will in general change the spin. And we also have, we have two kinds of SUSY transformations. We have the left-handed ones, and we also have the right-handed ones. Okay. Okay. So in a general, supersymmetry transformation changes the spin of the particle. Okay, so that's the novel thing about supersymmetry. It relates by the symmetry to particles with different spin. And then, so it changes the spin. One thing it does not change, so while it changes the spin, one thing that supersymmetry does not change is the mass. So how do we see that it doesn't change the mass? Well, so with Shih transformation, doesn't change the mass. And so that's a one-line argument. Okay, the mass is given by p squared. The mass of a particle is given by p squared, right? And well, I didn't write it here, but another part of the Shih algebra is p mu, as we said in last lecture, that it commutes with all the supercharges, right? So these are mutually compatible operators, right? In the language of quantum mechanics. So p squared, since p mu commutes with all the q's, p squared also does. Right? So if I act with q alpha on the field, or q tilde alpha dot, then I try to go, if I go measure its mass with p squared, I get the same mass as these two. Okay? So that's the one very basic thing about supersymmetry, which probably all of you have heard before, is that particles in the same supermultiplet have the same mass. And by the way, that's also how we know that supersymmetry can't be an exact symmetry of nature, right? Because we haven't seen all the superparticles or any of the superparticles, right? And if supersymmetry were an exact symmetry of nature, all those superparticles would have the same mass, as the standard model counterparts. Okay. Okay, so there are a number of ways to understand the irreducible representations of Shih. So I'm going to give you, very briefly, I'm going to give you two different ways. Okay? So the theorem of Shih. So we're talking about, say, a single particle. Okay, so if we have a single particle, or a collection of particles, as it's going to turn out to be, how does it fall into irreducible representations of Shih? It turns out there's a very simple trick to get that answer in like 2 lines. Okay, and so the trick depends on the details of the trick depends on whether the particle is massive or massless. Okay, so let's do the massive case. So if we're talking about just a particle, then its energy momentum is just a collection of numbers, right? So I can boost to the rest frame. Okay, if I boost to the rest frame, then p mu is just this. Okay, and yeah, so p mu is just this. And then in the rest frame of this particle, the Shih algebra just looks like 2m delta alpha alpha dot. Okay, in other words, in the rest frame, this just becomes sigma 0, which is just the 2 by 2 identity. Sort of like this. Okay, so does anyone recognize what this is? What is this algebra?
Creation and annihilation.
Yes, so these are just creation and annihilation operators. How many creation and annihilation operators? 2 copies of creation and annihilation operators, right? So this is Q1 dot equals 2m, and Q2 Q2 dot equals 2n, with everything else 0. Right? So these are creation, fermionic creation and annihilation operators. Okay, so the SUSY representation theory becomes something I've already solved a million times. Right? And so we know how to build up the irreducible representations of this. We start out with a vacuum, which is annihilated by all the annihilation operators. And then we act in all possible ways with the creation and annihilation operators until we get back to 0, right, by the Pauli exclusion principle. So basically, we start with the vacuum, and we hit it with one creation operator, with the other one. Okay, and I can't act with this twice, right? That would give me 0, or this twice, that would give me 0. And most I can do this one and then this one. Okay, and then okay, so that's 4 states in this box space, right? So that's 4 different states, and I also know what the spin of these states is, right? So suppose this this vacuum here has spin j. Okay, this is just angular momentum addition, right? If I start out with spin j and I add spin a half to it, that can give me j plus or minus a half. Okay, and then when I come back to here, this is actually a scalar object, right? This is like my epsilon alpha beta. So I get back to j. So if I rearrange this from decreasing spin to increasing spin, I can make a diamond out of it. Looks like this. Oops, it was that. Okay, so this is a massive, irreducible representation of SUSY that's now with the massive particle erect. Okay. So this could, for instance, describe matter fields, right? The standard model, supersymmetrized. Right? I could start off with, well, no, I'll get to that example in a moment. Okay, so that's the massive case. Now the massless case is slightly different. Massless case is different. Why? Because I can't boost the rest frame anymore. So the best I can do is, to go to say align in some direction, and we always like to go to the z direction, right? Okay, so if I go ahead and do that, I plug this into my SUSY algebra here, then, then I just have sigma 0 and I have sigma 3, right? And these are equal, so one part of the sigma 0 cancels out, the other part doesn't, and I'm left with just this matrix. All right. So, what is this? It's a little more complicated, but not really. They're still raising and lowering operators, but how many do I have now? Just one set of raising and lowering operators. So these guys, which used to be 1, are now 0. So these guys are just 0. They don't do anything. And then these are the raising and lowering operators. Okay, so Q1 dot are a pair of raising lowering. And Q2 are just 0. All right. So this says that the massless particle erects are smaller, so massless irrefs are smaller. And also, we don't get to talk about the, well, okay, so the massless irrefs, you start with a vacuum, and then you can only act with this raising operator, and then you're done. Okay, so the massless irrefs are described by, well, so we don't get to talk about spin anymore. We only get to talk about helicity, right? So the massless irrefs are described by helicity J and J plus a half. Okay, and then by CPT, the theory has to also contain another massless irref with helicity minus J and minus J plus a half. Okay, so people usually talk about the sum of these two massless irrefs, even though it's not irreducible, because they always come together by CPT invariance. All right, so this is the massless case, and this is the massless case. So now let's just work out a few examples, the ones that we're going to need. Okay, so one example is the massive case is, let's suppose we did J equals 0. Okay, so J equals 0 is a bit special because this doesn't exist anymore. There's no minus a half total spin, right? So J equals 0 is just 0, 0, a half as the degrees of freedom for the spin, right? So we recognize, so these are two real spin 0 fields. That forms a complex scalar. And this is one spin a half field, so that's one left-handed vowel fermion. Okay, so this is a complex scalar plus a left-handed vowel fermion. Or it could be a right-handed vowel fermion. Okay? And so these are, so if it's a left-handed vowel fermion, then we call this a chiral multiplet. And if it's a right-handed vowel fermion, then we call it an anti-chiral multiplet. Okay, both are possible. Okay, so we can also do massless J equals 0. We do massless J equals 0, we come here with the helicities, all right? And we see it's the same degrees of freedom. You have two zeros, and then the helicity can either be plus a half or minus a half, and that fills out the possible helicities for massless fermion. Okay, so this is the same. So there's no difference in the field content for a massive or a massless chiral multiplet. And that stands to reason. Okay. Any questions about that? Yes?
You parameterize this liquid space in J, and you choose, for instance, J equal to 0. But if we parameterize in a different way, like J equal to minus 1.5.
So the J here refers to the total spin of this vacuum here, the bottom state. So total spin can't be negative, right?
Well, the vacuum should be J minus 1.5.
Why? No, you're thinking, so the way I got this was I started with something to spin J, I acted with the superchargers this way and this way, and then I got back here. This was the vacuum. Yeah. So in this case, for j equals 0, going this way would have gotten me 0. Good. Thanks. Okay, so that's what happens for j equals 0. The only other case we're going to need is j equals a half. Okay, so let me do j equals a half. Okay, so for j equals a half, then I get okay, so I get 0, a half, 1. Right, as the total j's that are in my multiplet. And so for the massless case, so before I discuss what this means, let me do the massless case. Massless j equals a half. So here I have felicity plus or minus a half, and here I have felicity plus or minus 1. So does anyone recognize what this is? Or at least what this is? What particle has velocities plus or minus 1? Photon, right? Or in general, any massless vector boson. Right, so this is a massless vector boson, and it's by supersymmetry, it's married to a spin a half, massless spin a half field. Okay, so this is has the right matter content to, so first of all, this is called the vector multiplet. And it has the right degrees of freedom to describe a gauge boson, massless gauge boson, with its 2 polarization states, and the friend, which is called the gauge genome. Okay, so this is a gauge boson plus gauge genome. Now we come here to the massive case, and so what do we find? So this part here, so remember this total spin now, right? It's massive, so it can also have the zero spin, zero helicity polarization, if you like, right? So it can have 3 physical polarizations. So so this is again the analog of this, right? This is the analog of the vector multiplet, but massive. But now look what happened. We didn't just get that. We also got this. This is an entire chiral multiplet degree of freedom. Right? So what happened there? Why does the massive vector multiplet have your usual vector multiplet plus an entire chiral multiplet living in it? Anyone? Why should it have this extra degree of freedom?
Massive vectors do have an extra degree of freedom. Massive vectors.
Yeah, so think of the non-supersymmetric case. How does it? What's the only way a vector can really become massive? There's a Higgs mechanism where it eats a scalar, right? It eats the Goldstone bosons. So here it's doing the same thing, but it's eating an entire chiral multiplet. And so this describes a massive vector boson having eaten a chiral multiplet. Actually, it's not an entire chiral multiplet, I think. Did I lie? I may have lied. Because it doesn't have a complex scalar, just a real scalar. So it's like a Goldstone boson version of a chiral multiplet. And a little confused about that at the moment, but I think that's right. Okay, so
I think it is a whole chiral multiplet. One component goes in the hairy vector, and the other one is left over.
Sorry? You think there are 2 zeros?
And if you split that way, that 0 is two scalars.
2 scalars?
Yes.
Oh, yeah, of course. Thank you. So there's the jz equals 0 part of this one. Right? So this is, thank you. So good, it works. Okay. So there's the -1 and 1, which came from here, and then there's a 0, which, yeah. So there's a whole chiral multiplet degree of freedom. That's good. Phew. Okay, so this is of course right. So this is the somehow just by doing the representation theory, we have learned about the super Higgs mechanism. Okay. Okay, so that's generally where you stop. You stop at j equals a half, actually. And why is the reason for that? The reason is that if you go beyond j equals a half, look what happens. Your supermultiplet starts to include degrees of freedom that have spin greater than 1. Right? So if I do j equals 1, then I get all the way up to, I already get up to spin 3 halves. Right? So spin 3 halves, of course, could describe the gravitino, but any theory with spin greater than 1 cannot be described in a normalizable way. Okay? So if you're just doing field theory, you stop at j equals a half. If you're doing supergravity, you keep going. Okay? All right, so that's one standard way to derive the representations of different supermultiplets, and you get the chiral multiplet and the vector multiplet. Okay, so now I want to talk about another point of view on this, which is less standard, but which I find also very useful. Okay, because it's yeah. So I find this more useful. Not more. I also find this useful. Yeah, and okay. So what is this other point of view? It's to this is more like the follow your nose way of getting all the representations. Yeah. Okay. So another way you could generate all the representations is just by turning the crank. What do I mean by that? So another way to derive the representations. So let me just say derive the supermultiplets. Is to just keep acting with the supercharges until you can't act anymore. Okay, so start with a field. Let's just start with a scalar field, for example. Okay, so we want to fill out a supermultiplet that the scalar field is. Okay, so why not just keep acting with the supercharges and see where that leads you? Okay, so that's another way to do it. So if I act once with this, if I act once with the supercharges, I'll get just some new field with the spin a half, right? So let me just give this thing a name, call it psi alpha. Okay, I can also act, say, with this thing, with the right-handed one, and call that thing psi alpha dot. Look, I think I'm going to regret this. So start with this. Okay, so suppose I just did that, and then let me keep going. I can do it twice. So suppose I act on this thing now with Q alpha again. So I'm just filling out a multiplet. I don't care right now if it's reducible or irreducible. I'm just filling out a multiplet by following my nose. So if I act again with Q alpha, so this is Q alpha Q beta on 5. These are antisymmetric, right? So this thing has to be proportional to epsilon alpha beta. So this thing I call F. Well, to be more precise, I call this thing epsilon alpha beta F. Okay? And I can do the same thing over here with the Q tilde. Q alpha dot, Q tilde beta dot on pi. All right, so I won't, I'll spare you the details. So if I act in this direction with the Q, or in this direction with the Q tilde, then I get something with these indices. Okay? And I claim it doesn't matter in which direction I come, as long as provided I drop total derivatives. Okay? So this direction and this direction differ by the anti-commutator of Q and Q tilde, okay, which is a total derivative. So if I drop total derivatives, then it doesn't matter. Then this is the only new thing I get. Okay? And so this thing I can call A alpha alpha dot. Spin 1. Right? And if I continue in this way, dropping total derivatives, I find that, so first of all, I can't act again with Q tilde, I've used them all up. Right? By the anti-symmetry. So this thing is Q squared, Q tilde squared, and I've already used all of them up after that. Alright, so acting any further will give me 0. Acting any further will give me 0. And going in this way, I'm going to get going in okay, so going in this way, I'm either going to get back psi alpha dot, derivative of that, or I can get back something new, call this thing eta alpha dot. One over here. Oh, sorry, did I? No. Sorry, this one's an alpha. Alpha dot. And finally, when I come all the way down here, the last thing I do is when I've acted with all the Q's and all the Q tildes, okay? And so this thing I call D. So in this way, I fill out a diamond. Okay, if I start with spin 0, I fill out this diamond that has all these degrees of freedom. Okay, and because of the anti-symmetry of the Q's and the fact that their anti-commutator gives you a derivative, okay, if you drop the derivatives, this is all you can get. This is the most general thing you can get, starting from spin 0. Okay, so this also has a name, even though it's not an irreducible supermultiplet. So this is called, not surprisingly, the general supermultiplet, and it's reducible. Okay, so because it's reducible because it doesn't follow this classification that we just did. Right? It's much bigger than the irreducible multiplets we just derived. Okay, so we know it has to be reducible. So from this point of view, what does it mean for this thing to be reducible? Okay, it means that just like in any representation theory, it means that there's some subset of this. Okay, there's some subset of this which only transforms into itself under supersymmetry. Okay, so there's some way to isolate a part of this which only transforms into itself, and that would be the irreducible, representation, sub-representation. Okay, so you may have guessed, for instance, how does this thing decompose into a irreducible representation? So this is one thing you could do. Okay, so these look like a chiral. These look like a chiral multiplet, right? But it's clear that they don't transform into each other, right? There are ways to get out of that chiral multiplet. So the way to make this truly irreducible, turns out, from this point of view, is to impose what's called a constraint. Okay, so you don't consider the most general phi, right? So you don't consider the most general phi. This is an infinite dimensional representation, right? So you don't consider the most general phi, the most general function phi, but only one that obeys a certain constraint. Okay, that's how you select out the irreducible part of this representation. Okay, so the disadvantage of this approach is it's not as methodical and systematic as what I previously presented. Okay, but so it helps to have already gotten the answer. Okay, so but to get the irreducible supermultiplet, I must impose constraints Okay, so what is one constraint I could impose? Well, I could just say that, so for example, I could just declare that phi is annihilated by all the right-handed supercharges. Okay, if I declare that phi is annihilated by all the right-handed supercharges, that has a desired effect. Now I can't go this way anymore. If I try to go this way, I get 0, or I get a total 0. Okay, so so if I declare that phi is annihilated by all right-handed supercharges, I end up with just this part of my diamond. Okay, so I have phi, psi alpha, and f. Now, this is also puzzling, right? This should be puzzling to you. Looks like we have a paradox, because I'm telling you that this is one way to get an irreducible representation, but it looks like I've gotten too much. I've gotten my complex scalar field, I've gotten my Val fermion, but I've also gotten this thing F. Okay, so that paradox will resolve later when we construct Lagrangians. And we see that F actually is what's called an auxiliary field. So F, this is actually an auxiliary field. And what it means to be an auxiliary field is that it has no propagating degrees of freedom. It has no dynamics. Okay? And another way to say that is that it has no kinetic term. Okay, so when you do the path integral for F, it's just a trivial integral, not a path integral. Okay, so auxiliary field, in other words, no kinetic term. Okay. So in that way, it agrees with what we just did. Okay. So another type of constraint. Okay, sorry. So I should probably finish talking about this one. So this is again a chiral supermultiplet. But talking about it in this way, using fields instead of before where we were talking about particles. So using fields in this way, we get more. Okay, because we can do things to these fields now, right? So this is a chiral, phi is a member of a chiral supermultiplet. It obeys this condition. And so now we can, for instance, talk about products or sums. Okay, sum of two chiral superfields is equal to chiral, right? Because it's a linear condition. What about products of chiral superfields? These are also chiral because this condition here is a commutator. So it acts like a derivative, right? Commutators act like derivatives. Okay, so if phi1 and phi2 are both chiral, then their product is also chiral. Okay, and that is a key fact that we will need in order to construct supersymmetric Lagrangians later on. Is there more chalk? Okay. So products of chiral super fields are chiral. So we can also define what are called anti-chiral supermultiplets. So if phi is chiral, then phi dagger is anti-chiral. More generally, I can talk about some other fields, say phi tilde, which is annihilated by a left-handed supercharge. Okay, and so this would be phi tilde, and then this would have a right-handed Val fermion and auxiliary field. Okay, so products of anti-chiral supermultiplets. I haven't introduced what a superfield is yet. Products of anti-chiral supermultiplets are also anti-chiral, and then if I multiply together anti-chiral and chiral, it's nothing. Right? It's neither chiral nor anti-chiral anymore. Does anyone have any questions? Okay, it's all pretty dry stuff, but we're going somewhere with it. All right, so that's one type of constraint connected to the matter fields of the emphasis M. So let me do the other example that we're going to need, which are so another example are what are called vector supermultiplets. So again, so this is very simple. So all I say is that if I have a start with some, well, I'm going to call it v now instead of phi. Okay, I just declare that it's real. That's all. I declare it's real. So it turns out, so it turns out that is enough to get rid of enough degrees of freedom that this becomes irreducible. That is a bit harder to see, though. That is a bit harder to see, and I'll have more to say about that later when we talk about gauge interactions. But one thing which we can see, is, so by requiring that this is real, that kind of just percolates through this whole thing. Okay, so everything here pretty much, roughly speaking, becomes real. Okay, in particular, that has one good thing here, right, which is that this vector, here there was a vector, but it was a complex vector. Right, because I started with a complex scalar, and I get a complex vector. So now I have a real scalar, and it's a real vector, which is what you would need to describe a photon. Right, you would need a real vector. So this would imply that A of alpha is a real vector, and that's a desirable thing. But it doesn't seem to really kill off this multiplet and get us anywhere closer to the vector supermultiplet we had before, which was really just the gauginos, right, and this thing. All right, so what happens here, in order to reconcile these two pictures, is we haven't used any gauge invariance yet. Okay, but so any physical theory that has a massless vector in it is in general going to have gauge symmetry, right? And so we should be asking if this thing, we want to agree with the previous picture and we want it to be a gauge field, where's the gauge transformation? So a gauge transformation actually looks very simple in this picture. So if I shift V by the real part, or the imaginary part, it doesn't matter. So the imaginary part of a chiral supermultiplet, that preserves the fact that V is a vector supermultiplet. So then this is still satisfies okay, and so this turns out to be the gauge transformation in supersymmetry. Is I shift by the imaginary to real part of the kernel supermultiplet. And so using this gauge freedom, okay, if I build a theory that has gauge invariance, then I can use this gauge freedom. Turns out I can use this gauge freedom to set most of these things here to 0. Okay, and then after you do that, that's something called West-Umino gauge. And after you do that, that then emerges the degrees of freedom of a chiral supermultiplet. Sorry, vector supermultiplet that we had before, namely the gauge field and the gauge enos. Okay, but I'll be doing that in a later lecture. Good. And one thing, as we'll see, that's not possible to eliminate is this D here. Okay, so this D becomes another example of a auxiliary field. Okay. So, all right. So those are actually the only two examples. These are the only two supermultiplets that we're going to need, pretty much for the rest of the course: the chiral supermultiplet and the vector supermultiplet. But I just want to talk about one more supermultiplet that's close to my heart. So that is the supermultiplet that a conserved current lives in. And so that's what's called a real linear supermultiplet. So that's described by the following set of constraints we impose that is real, just like we did for the vector supermultiplet. But we also require that is annihilated not by 1, but by 2 actions of the supercharge. So I should probably write this. So that defines a real, yes?
So J here, is that every sort of individual thing in the supermultiplet?
No, this is just the lowest component. I'm changing the notation to this. So V is 5,
Okay.
and J is again 5.
But then it turned out that 5 was 0.
It turned out
that you could gauge it away.
For the West-Umino case, yes. Yeah. So 5 is pure gauge. Okay. So this, I claim, is what you would need to describe a conserved current. And so let's just see how that happens. So if I start off with J, well, okay, let me go back here. So if I start off with J, where does this stop? So it stops, so this becomes 0, and this becomes 0. Right? So if I act twice with Q, or I act twice with Q tilde, I'm supposed to have the constraints as I get 0. Okay? So what this selects out is this part of the diagram. So I have J, I have 2 fermions, J alpha and J alpha dot, and I have some J mu. Oops. J mu. And everything here is real, like a conserved current should be. Okay? So, right, so conserved current should be described by a permission operator. Right? So this here, I claim, also satisfies d mu j mu equals 0 as a consequence of these constraints. Okay, and this is going to be homework problem number 2, is to show this. Okay. So this is the supersymmetrization of a conserved current, and it's what's so this is the hero of the story when we're going to talk about plays an important role in something called general gauge mediation, which is all about coupling the MSSM to some hidden sector using the gauge interactions of the standard model. And the way you gauge a symmetry in general is you couple a vector field to its current. Okay, and so the coupling of the vector field to the current in supersymmetry is just J times V with some integral over superspace. Okay, so we can talk about that. So it's Q to the 4th. Oh, anyway, just getting ahead of myself. But it's in the way I'm doing it now, it's Q to the 4th. Okay. All right, so that's it for the super multiplets, seen 2 different ways. Any questions? Any other questions? Yes.
So when you started off at the very beginning, and you took the vacuum and you acted on it with both Q tools. So they're not formed. Do you not just get 1 degree of freedom from each one of those, i.e. 1 spin on one particular Z component of the spin?
I think that's not the right way to look at it. So you're saying, yeah. So when I hit this thing with full, this is a spin. This is a spin 1/2 object for percent 0 1/2. Okay. So the angular momentum addition tells me that I should get both J plus 1/2 and J minus 1/2.
Are those not Z components of spin?
No, that's total spin. And if you want to fill out all the different Z components, you have to also allow for the Z components of this, right? So this has Z components ranging from minus J up to J, and this has Z components minus 1/2 and 1/2. So you do the touch Gordon coefficients, etc.
Okay. So thank you.
Cool. Any other questions? Yeah.
Okay, can someone think of any other supermultiplet for besides you made this J? Or there is constraint because of these Q's and one cannot hit too many Q's.
That's the limitation, yeah. So you get 1 Q, you get 2 Q's, and then it stops. Yeah. So let's see, have I exhaustively mapped out all the different constraints? I think I have for the spin. So also it depends on what spin you start with, right? So if you start off with spin 0 as the top of your diamond, I think I have them all. And then you can get additional complications maybe if you start out with higher spin here. But that's not going to give you that's going to give you spin greater than 1 when you come down here. So yeah. Yeah, but the disadvantage of this approach is you don't see that it's not as you can never be sure with this approach necessarily that you map out all the possibilities. Right. So the other approach is more on top. Good. Okay. So I said I finished with the supermultiplets, but I guess so. There's one more very important subject I need to cover to really wrap this up before we could get down to the business of constructing Lagrangians. Okay, which is the powerful technique known as superspace. Okay, and this is often how the subject is presented first. Actually, so Uribe-Weissenberger basically starts with superspace. So, but these are all different perspectives on the same thing. Okay. So I'm talking about supermultiplets and supersymmetry transformations. So there's another way of describing the same thing, which is to sort of geometrize things. Okay? And so that is what superspace is. And in superspace, you basically turn the supersymmetry transformations into coordinates. Okay? And then your fields depend on these extra superspace coordinates. And so they become what are called superfields. And so this clearly is a very powerful approach, because a single superfield will now contain the entire supermultiple. Okay, so it's a much more compact way of describing things. All right. So the idea for all this is one starting point for how you motivate all this, other than what I just said, is that just like P mu corresponds to a derivative, right? When acting on any space-time field, corresponds to a derivative. The supercharges should be describable or representable as derivatives of some new coordinates. Right? All right, so new coordinates, obviously, because they're fermionic, and so they have nothing to do with the x mu coordinates, space-time. Okay, and so these coordinates are kind of funny, right? So if I'm supposed to write q alpha is like d by d, say some new coordinate on theta alpha, and also q alpha dot is like some other new coordinate, theta tilde alpha dot, then what are these coordinates? They're not regular numbers, right? They are Grassmann numbers, right? So these are not C numbers, but they're Grassmann numbers. They're anti-commuting numbers. Yeah. All right. So theta are Grassmann values, okay, which means they anti-commute with each other. And so we see we should have 4 of them, right? Theta 1, theta 2, and theta tilde 1, theta tilde 2. Okay, so that together with my x mu is what's known as superspace. Okay. Right. So this, of course, is wrong. Right? That's why I have the squiggles. So this is wrong. And why is this? Why is it not that simple? So why is this not the superspace? The representation of the q's in superspace? The answer is on the board. Yes?
There's two of them. You need to make a key wheels.
So this has to represent the algebra. Yeah? So this one and this one, anti-commutator, I have to spit out a derivative. But I just told you that these just plain old anti-commute, so they can't anti-commute. The derivatives can't anti-commute to anything interesting, right? The derivatives anti-commute to 0. So the way you represent the q's has to be a little bit more complicated if you're going to get the algebra. And so you can basically get the answer by by analyzing the index structure again. Okay, by Lorentz. So if I say that I definitely want to have the d by d theta alpha in the story, and I say what else can I add to this? So what else has an alpha index, and what else has an alpha index, and also is, is also fermionite? Pretty much the only thing I can do is this. Okay, you can sort of see how this, hopefully, how this is forced upon me. I don't get to, this is not a choice. Right, and then I fix the coefficient, so similarly, so I fix the coefficient here. So this is a cast of characters, okay? And the linear combination that I have to make here is dictated by getting this anti-commutator right. And so it turns out that I should put in minus I here, and minus I here, and then I get those anti-commutators. Okay, I am going to be a little bit more careful here, and I'm going to denote I'm going to distinguish between operators, which are the supercharges, and then their differential operators on superspace. The way that they're represented as differential operators in superspace. Okay. If you don't do that, sometimes you get tripped up. Okay, these are two different things. And so these have the same, okay, so they have the same commutation relations as the supercharges. Okay. Which you can check at home. Okay, this one's an easy one. All right. Okay. Yeah, that was an easy one. Okay, so those are how I represent the supercharges in superspace. And so I can talk about now a field, a superfield, which depends on my superspace coordinates. This is a superfield, so it's a field on superspace. Okay, and so the supersymmetry transformations. The reason I go through all this trouble is now the supersymmetry transformations of a superfield are really not good at drawing. Look like that. Are represented by the supersymmetry transformation of a superfield is literally just this differential operator acting on it. It's a total analogy with translations, right? Translations of a, that's why we go to fields, is then translations of a field are just the derivatives, are just a derivative acting on that. Okay. All right. So, so another nice thing about superfields is a lot of the things we went through before, including working out painfully this diamond for the general superfield, become completely automatic in superspace. So a lot of these treatments that start with superspace, you don't actually see why it's working. It's just because it's so automatic. So that's one reason why I like to go through the long way first. Okay, so what am I talking about? So for instance, let me just expand this thing before I even talk about what it is, let me just try extending this thing in superspace. Okay, so if I extend this in superspace, what does that mean? Well, as you know, so I'll stop writing these indices here. So as you know, cross-bond coordinates are very easy to work with, right? So they stop. Their Taylor expansions are very easy to work with because they stop because they're continued numbers, right? So if I just start expanding this thing, theta tilde, you know, I get at linear order I get that. At second order I get this. Right? At third order, it starts to get smaller. Oh shit, I'm not, oh well. My bars, my tildes became bars. And then at fourth order, there's only one thing you can do. Okay, lo and behold, so all of these are regular space-time fields, not superfields. Okay, and so we recognize now the general superfield, that diamond that we worked out before. Okay, before we did it really the most brute force way, but you see in superspace, it's automatic. Okay, so the claim, so what I just showed is if I take a general superfield that has no constraints on the superfield, and then I just expand it into thetas, I get that general supermultiplet that we had before. Right, so this is a general superfield. Okay. All right, so I don't have enough time to derive the chiral superfield, so I'll do that next time. But the chiral superfield was a truncated version of this, right? So the chiral superfield was just just this one, and this one. Okay, so it turns out a chiral superfield is a subset of this, theta squared f. Stop writing all that stuff. Plus total derivatives. Plus derivatives of these three objects, or actually just these two objects. Okay? And so, how do we get that? Sorry, this is the chiral superfield. And so, how we get this chiral superfield from the general superfield by imposing a constraint, we will see that how to do that in superspace next time. Okay, so let me just finish now.